In the second lecture here, we are going to continue with our revision on complex stresses. We'll use this example to discuss how to come up with the stress element. Now, the example here says we have a solid rod and it has a radius of 75 centimeters, sorry, 0.75 centimeters or 7.5 millimeters. It is subjected to the loading shown at point B. Now at point B, we can see that we have a horizontal force 500 newtons in the y-axis direction and also a vertical force of 800 newtons in the direction of minus z. So if you get a question, first of all, check the axis. If they give you the axis, use the given axis as your reference. If they don't give you this axis here, it's just a diagram, then create your own axis as reference. Okay, so now in this question, point C is built in, so it's fixed, and they want you to determine the state of stress at point A. So we have point A here. Okay, so if you look carefully, point A is located on the surface. It is on the plane of xy. It's on the surface in the x direction, right? And the plane is zy, okay, vertical plane zy. So the element there will be facing, the surface will be facing direction of x. So if we look at this question here, now to find the stress element here, first we need to determine what the stress element or this point experience. So we need to know what are the loadings at this cross section here first. All right. Now to do that, we take a section at point A. Okay, we take a section here. Now there's two ways doing it. You can use the free body diagram of the end here, the free end, from point A right until point B. Or you can also use the back here, the back portion, which is AC. You can use either one to determine your free body diagram. If you use point C, so you will have, not very good in drawing with this pad here, but you will have something like that, right? So that is point C, and over here you can then determine y, x, and also z. Okay, you can determine what are the forces acting at that cross section, right? So let's go to the next slide. Now this slide shows that, this slide shows that, sorry about that. It shows the free end from point A. So we have point A here to point B. So if we take the free end here, you have to determine what are the reaction forces and moments acting on this cross section due to the applied loads. So if we look here, the applied load 500 newtons has a radius arm of 14 centimeters. Within using that radius arm, it will be having a moment, right? A moment about z. So this is z here, vertical is z. So it will apply a moment about z. Therefore, the reaction on the cross section will be opposite direction, and that will be 500 times 14 here, right? That's the first action of this 500 newtons in the y direction. The other effect of this 500 newtons is the axial load acting on the cross section. That is 500 newton in the minus y direction, right? So those are the two effects of these 500 newtons at point B. So we have point B here, right? And here is point A. Okay, so we have two. One is this countering moment here, and the other one is the axial load acting at point A, okay, in the cross section. Then we go and take a look at this vertical force of 800 newtons acting on B, which is in the minus Z direction, right? So if you look carefully, 800 newtons, a perpendicular distance of 14 centimeters will give you a moment arm about this axis here. Sorry, this axis Z. Sorry, I'm mistakenly. Now why can't I remove that? Sorry about that one. No, forget about that. So we have 800 newtons times 14 centimeters will give you a moment about the y-axis, and that becomes torsion, right? So if you look from the y-axis here, so this is y at the end here. If you look from y, this is counterclockwise, right? Therefore, at the cross section here, you have a clockwise reaction. A clockwise reaction of 800 newtons times 14 centimeters. Okay, so that's moment about the y-axis. The other effect of 800 newtons is with this moment arm of 10 centimeters. So this 800 newtons will also give you a moment if we look from x direction. So remember, this is x direction, right? X-axis. If you look from x direction, this 800 newtons is giving a clockwise moment about x-axis of 800 times 10 centimeters. Therefore, at the cross section, we have a reaction, this reaction here, which is 800 times 10 centimeters. Okay, so we have this blue reaction here. Okay, and the other effect of this 800 newtons is a vertical force, right? Minus Z. Therefore, the reaction here is 800 newtons in the positive Z direction. So what do we have? We have a force here, which is shearing at this cross section. This is a shear force. We have axial load, 500 newtons. We have a torsional moment of 11,200 newton centimeters. We have a bending about the x-axis of 8,000 newton centimeters. We have a bending about the z-axis of 7,000 newton centimeters. So we have 1, 2, 3 moments, right? And 2 forces. So we have 5 components there that we have to take a look. So what are the effects of these 5 forces on the stress element at point A? Remember, point A is somewhere here, right? Is on the center line, okay, in the x-axis, is on the x-axis. Therefore, if you look carefully, now this 800 newtons is shear. And this point here is right at the neutral axis, right? So if we have a circle, remember we have a circle, then we have x-axis here, So here is X. Then we have, let me see, that is Z axis up there. And we are looking from Y, right? Y is the center here. So we are looking from the Y axis. So if we take a look, 800 newtons is going in the Z direction. Therefore, point A, this is point A here. Point A is at the neutral axis. So if we take this as the shear force, point A will experience the maximum shear stress. So what do we have? We have tau is equal to V times Q over IT. Remember? Now this will be shear. So we have tau is equal to VQ over IT. Right? So it gives you the shear stress effect. If we take a look at 500 newtons, 500 newtons is axial load. It gives you an average tensile stress, right? Therefore, at point A, you will experience an average tensile stress of P, which is 500 newtons, divided by A, which is the cross-sectional area of this circle there. Alright? Then we take a look at this moment here, which is torsional. We'll have a torsion effect on that surface. Okay? So if we draw an element, a rectangle there, okay, for A, we draw an element at point A. So that is Y. Upwards is Z, right? And X is coming out of that stress element. Okay. So that is point A. Now the effect of distortion here, 11,200 Newton centimeters, is going up, right, at the front here. So if this is A, on the left side, the shear is going upwards, right? That's the shear due to the torsion here. And this is giving you tau is equal to TR over J. Okay? Sorry, where's my T? That's T there. Okay? The top times R over J. R is the radius, J is the polar second moment of area. And that gives you this tau here, which is tau due to torsion. Okay? So this is tau T, right? Torsional stress. So on the left side here is upwards, therefore you have complementary on the other three surfaces. This is downwards here, right? Downwards. Then you have here is to the left, and here is to the right. Okay, so that's all tau due to T. So now we have one effect, two effect, three effect, right? Due to this 500, remember it's in the Y minus Y direction. So we have stress here. And so we have another stress here. And that is sigma due to 500. Okay? Those two there. We also have, remember 800 is upwards. So the shear stress, 800 is upwards. The shear stress is acting on the left side of the element. So if we have a stress element here, let's say we draw a box there, right? Sorry. We draw a box there. So it's on the left hand side of the box. So it's in the same direction. Therefore, what we then have is plus tau, right? 800, right? Sorry, it's going out of my screen. Tau 800 plus tau t. Okay, tau due to torsion. Now we are left with the other three. Sorry, the other two. This moment here, 7,000, and this moment here, which is 8,000. So now, if you look at this 8,000 here, this is a bending moment in the plane of YZ. Therefore, if you bend in the plane of YZ, in this plane here, right, YZ, this is Y coming out, and Z. If it bends in that plane, this here, point A, is on the neutral axis, right? So when it's on the neutral axis, it does not have any effect due to the bending, right? It's zero. So sigma bending due to this bending moment at point A is zero. So there's nothing there. Okay. However, this bending here, 7,000, is in the plane of X, right? X, Y. So it is this plane here, horizontal plane. If it bends in the horizontal plane above the z-axis and is bending clockwise if you look from the top, therefore point A is going to experience a tensile stress due to bending, and the point on the right here is going to experience a compressive bending stress, right? And so we know that this is the maximum bending stress for a circular cross-section is tensile due to 7,000 Newton centimeters. Therefore, is tensile at point A, so we have plus sigma due to 7,000. Okay, is bending stress. This is average normal stress. This is bending stress. M Y over I, right? Where M is 7,000 Newton centimeters. So you can change the units to Newton meters or Newton millimeters. It's your choice. Okay, so that is how we come up with the stress element here with combined loadings due to these two external loads. So first step is to find the free body diagram as shown with all the relevant reaction forces acting on the cross-sectional area, and then you find the effect of each one on the point of interest. In this case is point A. Okay. So this here shows effect of each individual loading or reaction forces. So we have the normal force effect due to 500. So you have 2.83 megapascal. We have the shear stress due to the shear force 800 newtons. Okay, it's 6.04 at point A. We have the bending moment due to 8,000 Newton centimeter, which is zero because it's at the neutral axis, right? We have a bending moment of 211.26. That's a bending stress due to bending moment of 7,000 Newton centimeters. And we have a torsional moment at point A, TR over J. Remember, due to this torque here, 11,200 Newton centimeters. So we have a shear stress. So if you take on the left side, this is on the section of AC. So the direction will be opposite of these directions here. Sorry. Okay, will be opposite of the ones we discussed earlier. Therefore, at point A, if you combine all these 5 here, we see that we have an axial normal stress 2.83 plus 211. Okay, we have a shear. On the right face is downwards, on the left face is upwards. Similarly for the last one here, this one here, on the right face is downwards, on the left face is upwards. So you just add them up because they have the same direction, right? That's the calculation given for effect of shear force. Then you have effect of bending of 8,000, which is 0, and effect of bending of 7,000, which is 211 megapascal, right? Then you have a torsional moment that gives you 169. Now these individual calculations are all based on solid 1. Everything you have learned in solid 1, right? So those are what you have done in solid 1. Those are the important things that you must have before we proceed to solid 2.